So continuing in our discussion for undetermined coefficients, using the superposition approach, we looked at a case 1 we called it, where our guess for a particular solution was not found in the complementary function. Okay, it was not duplicated in the complementary function. Well, let's start with an example where this might not be the case. Okay, so we have this differential equation here, and it has this auxiliary equation, okay, m squared minus 2m plus 1. This has repeated root m minus 1 squared. So our complementary function is what you see here. Now, continuing on our previous discussion, we would guess a particular form of a to the ex to match that. But unfortunately, that's taken already, okay? So when we plug this into here, we're actually going to get 0, okay? So it's not going to work out for us. This won't work out for us. So what do we do? Okay, and this is similar to the trick of repeated root. As we've seen here, this here is a repeated root. 1 is a repeated root. And how did we deal with that problem to get a second linearly independent function? We used the reduction of order method, and we found this linearly independent, second linearly independent solution for a second order equation. Well, these two are already taken. So what else can we do? What we're going to do is just multiply by another x. Okay, so we'll just multiply by another x. So this won't work. And if we multiplied by 1x, that still won't work because that's still part of the complementary function. But we multiply by yet another x, and we get this. And this will actually work, as we could see over here. So when we guess this form here for y particular, we have these derivatives of that, okay? And here the left-hand side is just given from the problem, e to the x is equal to this. Now this right-hand side is saying, well, take y particular and its derivatives and plug it into the differential equation, and you get this over here. And now match terms. Okay, and it turns out the right-hand side, when you simplify, this is 0 and that's 0, so the coefficients of these is 0. You get a bunch of cancellations, and you just have to match these two, okay? And so you get 1, which is over here, is equal to 2a, and so a is equal to a half, and y particular is this. The general solution then is the complementary function plus a particular solution, okay? So this is case 2, all right? And it's the case where a function in the assumed particular solution is also a solution of the associated homogeneous differential equation. How do you solve it? You solve it with the multiplication rule. That we call this the multiplication rule for case 2. If any ypi, so as we noted previously, that the right-hand side could be a sum of multiple terms, okay? So if any guessed assumed particular form that we have here, okay, so if any of these ypi's contains terms that duplicate terms in yc, okay, just as we had above there, then that ypi must be multiplied by xn. And what is xn? Well, where n is the smallest positive integer that eliminates that duplication. So pretty straightforward, okay? Here n was equal to 2 because that eliminated the duplication. When n equaled 0, well, that ran into a problem with this term. And then when n equals 1, it ran into a problem with this term, but n equals 2 worked, okay? So where n is the smallest positive integer that eliminates that duplication. We don't have an x squared. If we had an x squared e to the x here, we would have to go to x to the 4th and so on. So let's look at another example. We have, this time we have an initial value problem. And we follow similar steps as we've done before. The auxiliary equation here is m squared plus 1 equals 0. This has complex conjugate roots, plus or minus I, the imaginary number. And our complementary function would equal this, okay, in that case. So what initial guess would we make? Well, for this, we would have a ax plus b. But for this, we would have c cosine x plus e sine x, okay? Now here's a problem, right? This shows up in the complementary function, okay? So they have the same form. That's the problem, okay? It's, you know, it's not these letters here, the constant coefficients, okay? But you know, you could fix these constant coefficients to whatever you would find here, all right? So the problem is the form. This form is the same form as we have here, so that doesn't work. yp2 duplicates the terms in y complementary. So y particular then is ax plus b plus, what did we do? Just multiply by an x, okay? Each of the cosine x and sine x, okay? So we multiplied by x. That gets rid of the duplication. This here does not show up here, okay, with this extra x in there. And then we just do what we've done before. Here the right-hand side is from the differential equation. Here is taking y particular here, okay, that we guessed here, and plugging it into the differential equation to get that right-hand side. We end up with these equations here, which give us these solutions for A, B, C, and E. And so we fix those, and now we have our general solution, y complementary plus, you know, this 4x, that's the A, which you found here. B was equal to 0, so nothing shows up there. And then we have C here, that was -5, and that's why you get a -5x cosine x. And E was found to be 0, so that's why we don't see an x sine x term over here. So we got our general solution, but you know, this problem is an initial value problem. So what do we have to do? We have to satisfy the initial conditions. Okay, these are the initial conditions. We must satisfy them. What must satisfy them? The general solution, okay? This is not yp or yc, okay? This is the general solution. That's a common mistake. You have to take this whole thing, including the particular solution, okay? So if we take the derivative of y, we get this over here, and we're going to apply the initial conditions. The first one, so this is just coming from the problem in pink, that needs to equal what happens when we plug pi into our general solution, okay? And notice this is the whole general solution. So these terms come from the complementary function. These comes from the particular solution. And we get that. Solving, we get C1 is equal to 9 pi. Now we apply the second condition to the derivative, right? It's coming from the problem. This is y prime that you see here with pi plugged in. And we solve and we get C2 equals 7. And so we fix our constants and we get that this solution here not only solves the differential equation, but also respects the initial conditions, okay? And I write here, notice that to fix C1 and C2 for a solution to IVP, we use the general solution, not YP alone or YC alone, okay? The common mistake here is to say, oh, well, you know, I only need to fix C1 and C2, so let me apply, you know, just Y complementary to the initial conditions. That would be a grave mistake. The initial conditions are for Y, okay? So you're going to have to include the particular solution, okay? As we have done here. We've included terms from the particular solution, not just the complementary. And so that's how you solve initial value problems use, for non-homogeneous linear differential equations with constant coefficients and with g of x of a form of exponential, sine, polynomial, or sums and products of this. This is called the method of undetermined coefficients, and we just looked at the superposition approach, and it's called the superposition approach because we could do this linear sum for each of these different terms, so we just call it the superposition approach.